I'm Mrs. Campbell, and today we're going to be talking about integers and rational numbers. Let's jump in. Integers are the counting numbers, 1, 2, 3, and the negative opposites of those counting numbers, -1, -2, -3, and 0. There's an infinite number of integers, and examples are 0, 3, 76, -2, etc. Here's an example. Compare the numbers 2 and -5. If a problem asks you to do that, all you have to do is plot the two numbers on a number line. And they're there. Now we can compare integers by noting which is the greatest and which is the least. The greatest number is the farthest to the right, and the least is the farthest to the left. In the diagram above, we can see that 2 is farther to the right on the number line than -5, so we can say that 2 is greater than -5. And we use this symbol, the greater than symbol, to mean greater than. Take a look at this little frog. He's sitting perfectly on top of number 7 on a number line. The frog jumps randomly to the left or to the right, but always jumps a distance of exactly 2. Describe the set of numbers that the frog may land on and list all the possibilities for the frog's position after exactly 5 jumps. So the solution to this problem is that we're going to graph the frog's position, and we're going to also indicate what a jump of 2 looks like. We see that one possibility is that the frog lands on 5. Another possibility is that it lands on 9. It's clear that the frog will always land, though, on an odd number. So, after one jump, the frog could be on either the 9 or the 5, but not the 7. After 2 jumps, he could be on 11, 7, or 3. By counting the number of times he jumps, we can determine where he lands. After 5 jumps, there are many possible locations for the frog. There's a systematic way to determine the possible locations by how many times the frog jumped to the right and how many times he jumped to the left. And here we have. So we've like R if he jumped 5 times to the right. Or L, 4 jumps to the right, 1 jump to the left, and so on and so forth. And that would tell you where the location is. So these are all the possible locations of the frog, and then you can see it written out as an equation over here. 5 jumps to the right would be 7 plus 5 times 2 equals 17, and that's where he would be. All right, let's talk a little bit about classifying rational numbers, just as a good review. When we divide an integer by another integer, non-zero number, we get what we call a rational number. And this is because it is the ratio of one number to another. So for example, if we divide one integer, a, by a second integer, b, the rational number we will get is a over b, provided that b is not 0. It's important. When we write a rational number like this, the top number is called the numerator and the bottom number is called the denominator. And you can think of a rational number as a fraction of cake. If you cut the cake into 6 slices, your share is a of those slices. So take a look at some graphics here. So for example, when we see the rational number 1/2, we imagine visually cutting a cake in 2 parts, and it looks like this. And this is what 3/4 looks like, and this is what 9/10 looks like. Now, proper fractions are rational numbers where the numerator or the number on the top is less than the denominator, the number on the bottom. A proper fraction always represents a number that's less than 1. And with a proper fraction, you would always end up with less than a whole cake. Improper fractions are rational numbers where the numerator is greater than the denominator. Improper fractions can be written also as mixed numbers, an integer plus a proper fraction. An improper fraction represents a number greater than 1. Now, equivalent fractions are 2 fractions that give the same numerical value when they're evaluated. So, for example, take a look at this visual representation of the rational number 2/4. Looks familiar, doesn't it? Yeah, because it's the same as 1/2. So you can see that it is exactly the same. And we can write out the prime factors of both the numerator and the denominator and cancel matching factors that appear in both the denominator and the numerator. So 2/4 equals 2 times 1 over 2 times 2 times 1. Cancel out those 2's, then you remultiply the remaining factors, and you get 2/4 equals 1/2. This is called reducing the fraction or writing the fraction in lowest terms. Now, reducing the fraction does not change the value of the fraction, it just simplifies the way we write it. When we have canceled all our common factors, then we can say that our fraction is in simplest form. Here's an example. Classify and simplify the following rational numbers: 3/7, 9/3, and 50/60. So with the first one, 3 and 7 are both prime. So there's not a simpler form for this rational number. So 3 over 7 is already in its simplest form. How about this one, 9 over 3? Well, 9 equals 3 times 3, and 3 is prime. So we just rewrite the fraction and with its prime factors, cancel out those 3, and we get 9 is greater than 3. So 9/3 is an improper fraction, and it simplifies to 3 over 1, or 3. Now with the one that says 50 over 60, 50 equals 5 times 5 times 2, and 60 equals 5 times 3 times 2 times 2. Rewrite the fractions thus, 5 times 5 times 2 times 1 over 5 times 5 times 2 times 2 times 1. And we get that 50 over 60 is a proper fraction, and it simplifies to 5/6. We also need to know how to order rational numbers. Now, ordering rational numbers is simply a case of arranging numbers in order of increasing value. We write the numbers with the least or most negative and the greatest or most positive last. So for example, put the following fractions in order from least to greatest: 1/2, 3/4, 2/3. The solution is 1/2 is less than 2/3 and 2/3 is less than 3/4. But how do we compare more complex fractions? That one's pretty easy. So how about this one? What's greater, 3/7 or 4/9? So in order to determine this, we need to find a way to rewrite the fractions. And what we're going to do is we're going to find the lowest common denominator. So the lowest common multiple of 7 and 9 is 63. Our fraction is going to be represented by a shape divided into 63 sections. This time we'll use a rectangle cut into 9 by 7, or 63 pieces. 7 divides into 63 9 times, so 3 over 7 equals 9 over 9 times 3 over 7 equals 27 over 63. Note that multiplying 9 over 9 is the same as multiplying by 1. Therefore, 27 over 63 is an equivalent fraction to 3 over 7. Here it is shown visually. So you can see 9 columns, 7 rows, and 3 rows of 7. 9 divides into 63 7 times, so 4 over 9 equals 7 over 7 times 4 over 9 equals 28 over 63. So 28 over 63 is an equivalent fraction to 4/9, and here that is shown visually, 4 of 9 columns. So by writing our fractions over a common denominator of 63, you can easily compare them. Here we take 28 shaded boxes from the 63, from our image of 4/9 above, and we arrange them in a way that makes it easy to compare with our representation of 3/7. Notice there's one little square left over right there. So the solution is, since 28 over 63 is greater than 27 over 63, 4/9 is greater than 3/7. Let's also talk about how to find the opposites of numbers. Every number has an opposite, and on the number line, a number and its opposite are opposite of each other. So in other words, they are the same distance from 0, but they're on opposite sides of the number line. So and also by definition, the opposite of 0 is 0. So for example, find the value of each of the following. What is 3 times -3? Plus. 3 plus -3. 5 plus -5. Negative 11.5 plus 11.5. 3 over 7 plus -3 over 7. Probably already figured it out. The value of all of them is 0. How about this one? Find the opposite of the following. 19.6, -4/9, x, xy squared, and x minus y. So, also pretty easy. If it's a positive number, it would then be a negative. Negative numbers would then be positive. So 19.6 is -19.6. -4/9 is 4/9. X is -x. Xy squared is -xy squared. And the opposite of x minus 3 is -x minus 3. Here's an important note. With the last example, you must multiply the entire expression by -1. Common mistake in this example is to assume that the opposite of x plus 3 would be x minus 3 would be x plus 3. So be sure that you don't make that mistake. All right, last thing we're going to talk about in this lesson is absolute values. So when we talk about absolute value, we're talking about distances on a number line. So for example, 7 is 7 units away from 0. The number -7 is also 7 units away from 0. The absolute value of a number is the distance it is from 0, so the absolute value of 7 and the absolute value of -7, both of them are actually 7. So we write the absolute value of -7 like this with these lines. And we read the expression, the absolute value of x, like this, the absolute value of x, just like I just said. We want to treat absolute value expressions like parentheses. If there's an operation inside the absolute value symbols, evaluate that operation first. The absolute value of a number or an expression is always positive or 0. It cannot be negative. With absolute value, we're only interested in how far a number is away from 0 and not the direction. So quickly, we can evaluate the following absolute value expressions. So the absolute value of 5 plus 4 would actually be the absolute value of 9, 9. 3 minus the absolute value of 4 minus 9 would be 3 minus 4 minus 9 is the same as 3 minus the absolute value of negative 5, which is 3 minus 5, and that gives us negative 2. Number 3 says, what is the absolute value of negative 5 minus 11? It's actually going to be absolute value of negative 16. The absolute value of negative 16 is 16. And negative absolute value of 7 minus 22 is the absolute value of negative 15. Negative 15, negative 15. It's actually super easy. Absolute values, I think, super fun. All right, guys, that just about does it for this lesson. Thanks for joining us. We'll see you next time. Bye-bye.